All right, I'm ready. I love tubes. I love old tube equipment, but there's one family of tubes that I don't like, and that's power rectifiers, because they're big, they're hot, they take power, and the job they do can be done by solid-state diodes. Okay, yeah, I wanted to show you this one. Pretty mercury vapor rectifier. Yeah. Here's another pretty one, another one of my favorites. But you can make a module like this and take your tube out, plug this right in, and it'll work. As you can see, there's diodes, 2 strings of diodes. There's resistors and capacitors across them to compensate for possible switching time differences. There's a big resistor on the back, the bottom there. I'll tell you more about that. This is what it looks like in a device. This is actually an HP 200 audio oscillator. This is that module in there. It's working. Here's one in a vacuum tube voltmeter. This one's a little different. This is just straight diodes, no resistors, capacitors. Can you see the value of that big resistor there? That's a 200 ohm, 5 watt resistor. Let's make note of that. Here's an example of making a replacement with terminal strips underneath the chassis. This is a little bit different. There's what the diodes and resistors and capacitors look like. This is a little messy, but this works. And here's another somewhat simpler example. You can see the 75 ohm resistor there. And I think that's it. Okay. So let me get rid of this. And we'll start the real show here. Okay. Yes, I hate power rectifiers. And this is why. Well, heat. Okay, they're big, they're hot. The power rectifier is usually the biggest, hottest tube in the whole box, the whole device. The filament for a vacuum tube rectifier is usually separate, and it's got the high voltage on it, so there's potential problems there. And they're tubes. They have cathodes. They're eventually going to go weak and go sour. They also have a fairly high voltage drop. Germanium diodes are 0.3, silicon diodes are 0.7. High vacuum rectifiers are like about 50 volts. Even mercury vapor rectifiers have some voltage drop, like 5, 10 volts or so. But that's a pretty high voltage drop. Some nice things about tubes is they can handle high voltage, especially peak inverse voltage, reverse voltage. They can handle voltage spikes and transients a whole lot better than solid-state diodes can. Obviously, they're not ESD sensitive, and they don't mind being around other hot tubes. If you are a rectifier replacement like this, you might not like being around other hot tubes. But here's the thing that you can make. This is an example of a replacement for a 5U4 rectifier. You can see that there's 2 series strings of diodes here. The diodes are in series so that they can handle greater peak inverse voltage. You can see the resistors and capacitors in parallel. That's to compensate for possible differences in switching time so that one diode doesn't all of a sudden have all the reverse voltage across it and avalanche and blow up. This resistor here to compensate for the voltage drop, that's a little bit of a problem. That's one thing I don't like, but I'll tell you how to deal with that. Now, I wish that someone would have explained this to me a long time ago when I started getting into electronics and radio. How do these rectifier power supplies work? Yeah, I wish someone would have explained it to me about a dozen times until I finally got it. I also wish I could show like all 3 of these at the same time. But let me just show you this. This is a full wave center tap power supply. You can see that the transformer has got a center tap that goes to the ground, the common negative, the chassis. The business end of the transformer winding goes to the anode of a pair of diodes. The cathodes are connected together, and that's what goes to the filter capacitor. So it's a full wave center tap. It's two half waves back to back, or top to bottom, depending on how you look at it. The vacuum tube supply is a little different. You can see, same thing, transformer is a center tap. The business end of the transformer goes to the plates of vacuum tubes. Now your favorite 5-volt vacuum tubes like the 5U4, the 5R4, the 5Y3, they have two diodes. You can actually see them. There's two of them inside one glass envelope, kind of like an integrated circuit. It's got more parts in one package. Okay, the filaments are connected together in series. There's two filaments, one for each plate. Sometimes, as far as the schematic goes, you will see this drawn as just one cathode, but it's actually two cathodes, two filaments, and they're in series. Now here's the part that I have some trouble with. The filament is powered by a separate 5-volt winding here. It has its own private, separate 5-volt winding, just for this one tube. Boy, isn't that something. But now this filament is hotter than heck, and it's got electrons flying off of it all over the place. And this plate, this anode, is pulling the electrons off, so it becomes positive. First of all, pulls off one side, then pulls off the other side, then this side, then that side. Okay, so the positive, the rectified voltage appears on the filament, and it also appears on the filament winding. So, yeah, this winding has to have a lot of insulation around it. Well, so does this one, but, you might think that this is just an ordinary little 5-volt winding. You don't have to worry about insulation, but you do, because this has got the rectified B plus on it. It's got to be insulated from the core, it's got to be insulated from the other windings, it's got to be insulated from the case of the transformer, it's got to be insulated from everything. And if it's not, you could run into some real problems, which I'll talk about later. And then that, go back, where is this? It's one side of the filament that goes to the filter capacitor. One side or the other. Which one? Well, it's one side or the other. I was thinking that there might be a convention or a routine connection, like, I thought, it's pin 8. They always use pin 8. Well, no, they don't, because there are some that use pin 2. I can show you later. It's one side or the other. And I was thinking, wouldn't it make a whole lot more sense to connect it to, like, the center, the middle of the tube? Well, yeah, that'd probably work, except that you'd need another lead coming out of the tube, and, maybe they don't want to do that. I was also thinking, since the filament winding has the rectified B plus on it, wouldn't it make sense to take it from the center tap of the filament transformer? That'd work too, and there are some devices that actually do that. It's not real common, but most of the time what you'll see is that the filament goes from one side or the other. Okay, just in quick review, the B plus supply that most tube devices have is a full wave center tap configuration. The rectifier tube has got two sections. It's a directly heated filament cathode. The AC that goes to the plates is a transformer winding with a center tap. The transformer also has the filament AC source that's a separate, well-insulated winding from the transformer. So remember that the filament winding, they all have the rectified AC, the rectified B plus on it. Okay. Also, I'm trying to think of all the good old AM transmitters of the good old days that have high voltage supplies with mercury vapor rectifiers, like those pretty blue ones I showed you. There's the Johnson Valiant, there's the Johnson Viking, there's the Barker and Williamson 5100B, which is one of my favorites. There's the Invader 2000. Those have a B plus supply for the exciter stages and stuff and such, but they have a high voltage supply for the power amplifier, modulators, whatever else, and often they have mercury vapor rectifiers. This is the same sort of critter. It's a little bit different because often instead of just one tube with two diodes, there's a pair of tubes, a diode apiece. Same thing, they have directly heated filaments rather than a heater and a cathode. And oftentimes you'll find that these are wired in parallel. The nice thing about mercury vapor rectifiers is that they don't have the high drop, voltage drop, the loss that these high vacuum rectifiers have. These might be, as much as like 50 volts. Mercury vapor rectifiers, 5, 10, something like that, handful of volts. A little bit of loss, not a whole lot. Again, here's what they look like. Same thing. The power transformer is a center tap. The center tap goes to the chassis, common negative. The business end of the transformers goes to the plates, the anodes of the tubes. Now, on the schematic here, you'll see these, the ones that have pins on the top. There's a little square or a rectangle up there to indicate that it's a plate pin on top. This little dot indicates that there's something inside the glass envelope besides nothing. That indicates that it's mercury. Here again you can see the filaments have their own separate winding. They're wired in parallel, and the filter capacitor is taken off of one side or the other of them. All right, these big monster transmitters also often have a bias supply, a negative supply for the negative voltage, for grid block keying, for amplifier bias, things of that sort. Again, a similar sort of critter, but again, this is a negative voltage. Same thing, it's a full wave center tap. Often, these rectifier tubes have indirectly heated cathodes. They have a heater and then a cathode around them. I'll show you why. The AC source is often the same winding as the B plus source, except it's a tap. You only need like 100 volts or less for bias, so it's a lot less. And again, the tube connections go the other way because this is a negative reference to ground supply. So the voltage, well, let's take a look at this here. Yeah, the transformer connection, the tap on the transformers goes to the cathodes, and they're indirectly heated cathodes. Often it's the same 6.3 volt supply that all of your other 6.3 volt tubes use. So if you get this thing out of here, that's like maybe an amp or so of current draw that you don't have on the 6.3 volt filament winding. The plates are separate, but they're connected together outside of the tube, and the filter capacitor, of course, is upside down. The positive end goes to the chassis, and the negative end goes to the rest of the circuit. Okay, let's get these things out of here, and I'll tell you how to do it. But before you start doing this, you got to take a look at the piece of equipment that you want to do this to, and it helps if you know as much as you possibly can about it, especially the power supplies, how it works. Oftentimes, it's as simple as deciding whether or not you want to have a plug-in module on top or a terminal strip on the bottom. But now remember, with the solid state supply, you throw that switch, you've got the B plus on all those tube plates all at once. And that could cause some weird things to happen. My favorite example is the Hewlett-Packard FR38 frequency counter. Okay, this is a digital frequency counter with vacuum tubes, and it's got neon decade displays, 0, 1, 2, 3, 4, 5, the columns of neon lights like that. You guys ever seen anything like that? Mm-hmm. Not the Nixie tubes, that's the new ones, but this is an old one with columns of neon lights, 1, 2, 3, 4, 5. But this one also has a pair of meters for the ones and tens place. The first two places, they want them to count real fast, so they're actual meters with magnets and coils and pointers. Normally, they sit at 0 center, and they go, 1, 2, 3, when they count. It's kind of fun to watch. But the way it normally operates is you throw the switch on this thing, and these meters, as the tube warms up, they will reverse pin, and then they'll come up with a random number, and then they'll reset to 0 as soon as a valid reset pulse comes along. So I make this solid state replacement, and I throw this switch, and all of a sudden I look, and these meters, they immediately reverse pin, and they stay reverse pinned. And I look at that and I say, well, that's maybe not the best thing in the world for them, although they seem to have survived all these years. In contrast, there's the Hewlett-Packard vacuum tube voltmeter. Now, normally, with the tube in it, you throw that, the switch, it starts to warm up, the meter hits the positive pin, and then comes back to 0. Now, with the solid state replacement, I throw that switch, the tubes start to warm up, the meter goes, about half scale, and then it comes right back down again. Better. I'm guessing maybe that's because the gas-filled regulator tube strikes right away, and it has a valid reference voltage on it for the regulator circuit in the power supply. So instead of going wild and then coming back, it behaves itself immediately. So, yeah, it helps if you know a little bit about the piece of equipment that you're dealing with, especially if it's got meters with needles. Another family of examples is receivers with S meters. Yeah, there's the National NC303, the Hammerland, I think there's an HQ180 and HQ150. There were a bunch of them that we did. And they have the backwards meters, where the meter actually sits at full scale, and when you zero it, it's actually, well, anyway, it goes backwards. But there's a couple of those that I think we also ran across this problem, where you give them a solid state rectifier, and they immediately reverse pin, and they stay that way until the rest of the tubes warm up. So keep in mind, funny things can happen when you solid state a tube type power supply. So yeah, you got to take a look at the device. Oftentimes, yeah, just are you going to do a plug-in on top or a terminal strip on the bottom? I like the plug-ins from the top. They're actually a little bit easier. And then, consider how the operation of the device could be changed. If you happen to have a plug-in module from a other previous project, you can just take it, plug it in, and see what happens. Makes things a whole lot easier. And then, as long as you got to take the thing out of the case, you might as well get out your voltmeter and measure the B plus voltage, measure the AC from the transformers if you can. One word of caution: if you measure the voltage and it's a whole lot lower than you think it's supposed to be, maybe it's because you got a weak tube in there. Maybe it's that that tube's starting to lose its emission, the filament, the cathode is starting to go sour. That might happen. B plus is going to be anywhere from like 285 volts to 350. It's going to be somewhere around 300. So yeah, measure it. Take a look at what the manual says. service documentation. Get as much of that as you possibly can. And now, with that information, you can calculate what the voltage drop from the across the rectifier tube is and or should be, and you can also get an idea of what that big series resistor is going to have to be. If you know how much current the thing draws, or how much approximately, it'll give you a ballpark idea of what you might need for that series resistor. Most receivers are like 100 milliamps, tenth of an amp. And most of the times, the resistor is going to end up being around 100 ohms. A little bit more, maybe 200, like you saw. A little bit less, maybe 75, could be. Then it's time to figure out how many diodes you're going to need. Remember that long series string where I had like 4 of them? Okay, well, if those are, 1,000 PIV apiece, well, that's like 4,000 volts. Well, the transformer might not even be 1,000. But it's a good idea to have a little bit of reserve. Actually, it's a good idea to have a lot of reserve because transients and spikes can come along, and if they're like really high, they can put your diodes into avalanche, and they can short and blow fuses and all sorts of terrible things. So I'd like to figure out, what the peak inverse voltage is going to be. Take the RMS voltage from the transformer, multiply it by the square root of 2, and get an idea what the peak voltage is. Then multiply by 2, or multiply by 2.5, or give it as much headroom as you possibly can. And when you put diodes in series, they also recommend that you put resistors and capacitors across them to equalize the voltage in case, switching time might be a little different. There's another family or a school of thought that says don't even bother with them, because if they're the same diodes from the same batch, they'll have pretty much close to the same reverse recovery time, and you won't have to worry about it. With 2 of them, yeah, I've done it, as you've seen, without the resistors and capacitors, and it'll work just fine. For now, I hope. But for more, for like 3 or 4, it's better to use the resistors and capacitors for insurance. That big hot series resistor, you figure 100 milliamps through 100 ohms, that's 1 watt. But still, 1 watt is a fair amount of heat. I happen to have a whole bunch of these 100 ohm 10 watt resistors, and I like to use these because a 10 watt resistor dissipating 1 watt of heat, that's not too bad. Also, if you're going to make a plug-in, you need a base, like what the tube has. If you're lucky, you can find these things at a ham fest. I bought a whole bunch of these. These are octal plugs. These are 8-pin plugs. Same thing as a tube base. Otherwise, what you can do is take this and go, oops. Yeah. Oh, well, at least the base is still good. And you can crack the glass away and then get your big hot soldering iron out and then pull the leads out. And you should probably do it with a paper bag and the pliers and crush it like that. And had to do that a couple times. But if you can find these, it'll make your life a whole lot easier. For the actual diodes, my favorites are 1N4007s. They're 1 amp, 1,000 PIV. You can get them from DigiKey. You can get 100 of them for $5. So that comes out to like 5 cents a piece. And 100, boy, that's a lifetime supply of diodes. For the resistors and capacitors that go across them, some of these .01 ceramics that I like to use, these are pretty big. A value like 0.0047, you know, half the capacitance, half the size, maybe, you know, that'll work too. For this resistor, somewhere around half a meg is fine. It just has to be a voltage divider to equalize the voltage spread. 470K 1/8 watt, quarter watt resistors, that'll work fine for this application. And also, it's nice to be a junk collector and have a junk box full of resistors like this. There's also a bag over there. Have you seen it with power resistors? You know, some of them might be useful in a situation like this. Like I say, it's going to be around 100 ohms, and if you can get a 5 watt, 10 watt resistor to dissipate a watt or two of heat, that'll work out a whole lot better. All right, here's kind of an expanded view of an assembly that goes into an octal base like this. What I do is I put the resistors and capacitors on first, the equalizing resistors and capacitors. I put them on first and solder them, because that's a lot of heat. Then I put the diodes on. Well, for two reasons. I don't have to use as much heat to solder the diodes, and of course I use a heat sink like an alligator clip or them fancy aluminum spring-loaded thingers, if you're lucky enough to have one of them. Also, if something does go wrong, if the diodes do zorch from a transient or a spike and they're short-circuited and you want to fix this, at least you can take the diodes off without having to worry about the wires from the resistors and capacitors. And then the next thing you have to do is figure out where to put this big hot resistor so that it's not too close to the diodes. Now, what I do is I build it up to this point. I get the two strips of diodes, but I don't put the series resistor in yet. What I'll do is I'll clip lead in, use clip leads, and put in a 100 ohm resistor and see what happens. Oh yeah, when you do this, oftentimes you'll have your module built up. It'll be a plug-in. One clip lead goes to the top of that set of strips, and then the other end of the resistor, well, you got to figure out where that goes, because that's going to be one side or the other of the filament connection. In the case of a 5U4, it's either pin 2 or pin 8. So you have to look at the schematic or look at the device and then use that as the connection. I'll tell you why. And of course, take a look at everything before you throw the switch. Because, again, we're dealing with high voltage here. Yeah, I know it's only like 300 volts, but still, be careful with it. Watch where your clip leads are going and things like that. Okay, now you get to throw it on, throw the switch, and give it a check. I, immediately look for smoke or sparks and things like that. But now, measure the DC voltage and compare that with what it's supposed to be. If it's close, well, then you're all right. And I always hope that a 100 ohm resistor will get me pretty close, because I've got a bunch of these and I can use them up. If it's not, then you might have to go to the junk bag and get a different value resistor and try to get a little bit closer. If it is pretty close to what you want, then you can continue. As an example, that HP 200 audio oscillator, 285 volts is the B+. I got 305. Okay, that's 20 volts more than what it's supposed to be. I figured that's okay. That's, the tubes are going to run a little bit warmer, but I don't have to try to find a 120 ohm resistor or something like that. Well, now Yeah, check your device under full load. If it's a receiver, like, crank up the volume all the way. If it's a transmitter with an exciter section, well, throw on the exciter or the spotter or whatever you can, and see what the voltage drops to under full load. And and you can also measure the voltage drop across that series resistor and get an idea of how much heat it's dissipating, how much current is actually going through it, a number of other things. If it's all right, you're in business. You can power everything down, take this resistor, solder it in, button everything up, and close up your case, and you can be happy because you'll have a piece of equipment that operates with about 10 or 15 watts less of heat. Oh, yeah, one thing I forgot to mention. These 5U4s are, the filament is 5 volts at 3 amps. That's 15 watts. 5R4s, I think, are 5 volts at 2.5 amps. Well, that's, okay, 12.5 watts. 5Y3s are 5 volts at 2 amps. So that's 10 watts. So you can save 10 to 15 watts of heat by doing this. That's, I think, the big advantage of doing this, besides not having to worry about your filament emission going sour and the voltage dropping and stuff like that. Okay, for your big power transmitters with mercury vapor rectifiers, it's similar, but it's a little different because you're dealing with much higher voltage. You probably are going to have to put 3 or 4 diodes in series and use the equalizing resistors and capacitors across them. For the middle item, series resistor, cross out probably, you won't need it. Don't worry about the series resistor for that. But of course, you've got 2 tubes, so you're going to need 2 modules. This is kind of a picture of what I have done. Yeah, this gets a little scary. Like the 866 rectifiers, that's a 4-pin base. Unless you can find them somewhere, yeah, you've got to crack a tube and pull the wires out and use a tube base. The terminal strip and everything here has got to be pretty rigid, pretty mechanically solid. The reason being that the top is going to be the plate pin where the cap makes the connection, and yeah, that's got to be pretty strong. You don't want that thing cracking at the base and falling over and short-circuiting to something. That could really be a mess. But here's an example of what we have done for the 866s, the Johnny Valiant, the B&W 5100B. Get them mercury vapor rectifiers out of there. You don't have to worry about the mercury. The filament is 2.5 volts at 5 amps. So that's 12.5 watts a piece. That's 25 watts for the pair of them. That's a lot of power that you can save by doing this. Bias rectifiers, don't forget about them. That's, again, similar, and in some ways it's a little bit easier. Now, the diodes go the other way, remember that, because it's a negative reference supply. You can probably get away with just one of these diodes per side. So, yeah, a pair of diodes. But now, remember, the bias supply is, 60, 70 volts, less than 100. So it isn't high voltage, and it isn't high current. The bias supply really doesn't have a lot of current drawn from it. All it has to do is sit on a grid and push electrons around. But now, the series resistor, you may end up needing 1,000 ohms or more to get it down to where it should be. And of course, after you do this, last item, It'll be the same as if you have to put a new tube in. Um, you might have to do the amplifier bias adjustments over again. Replace the bias supply. Well, we're just about done here. As I mentioned, in the configuration, the B+, the rectified B+, is on that filament winding. Well, now you don't need that filament winding because you don't have a filament. You can unsolder that power transformer if you want and get the B+ off of that winding, and a little bit extra insurance. You don't have to worry about it, insulation breakdown, arcing through other windings. Just make sure that you've got the right one, connected to the diode stack, or the other end of the resistor. Someone is going to ask me, well, what happens if you connect it to the other side? Well, the current is still going to flow through the winding, but then you're actually adding and subtracting 5 volts on alternate cycles? Yeah, I guess so. I've never done that. So I don't know what would happen. If someone does know, tell me about it. But this is another nice thing about making a solid state replacement. You don't have to worry about tube filaments. You don't have to worry about high voltage on the winding. You don't have to worry about the transformer failing. All right. Final word. If it does happen, and oftentimes it will happen, that the filament winding insulation will break down, there's going to be an arc from that filament winding to the high voltage winding, another winding, something. Anyway, it's going to go bad. We have run across basket cases, like receivers that have bad transformers. Oh, no problem. Well, just get another transformer, put it in, wire it up, and yeah, where are you going to get another transformer for a national NC303? You may be faced with a situation where you've got a basket case, you've got no other power transformers that will fit or will work, or the ones that will work won't fit, and you might be faced with having to rewind a transformer. Now, it can be done. It's not easy, and it's a whole other subject for another presentation some other time. But you may be faced with this, and when you are faced with this, consider that you can rewind that high voltage winding for exactly the voltage that you need. Then you don't have to worry about the voltage drop. You don't have to worry about this resistor here dissipating another watt or two. Just wind it for the voltage that you need. You could also consider maybe a single winding and using a bridge rectifier even. And of course, you don't have to wind the filament winding, unless you also have to rewind the 6.3 volt filament winding to take it off when you repair the transformer. So, there you go. That's it. Any questions? Well, yeah, you're first. You're closest.
I don't know if this is even a reasonable question. We talked about checking the B+ voltage. I'm expecting that there's going to be significant ripple on that. And do you do anything to check that? Do you look at it with a scope, or do you put, do you do anything to realize that there's ripple on that, on the B+?
Oh, I don't, because there's also the filter capacitor connected there at the same time. So yeah, I just DC.
This is more of a comment than a question, and it's just speculation. You might be able to cancel out some of that ripple with the filament winding if you miswire it backwards.
Right.
If you can get it out of phase.
I've wondered about that. I've never actually done it, because I'm careful. I make sure I get the right one. It's either one or another.
And you might put a diode bridge or something in that to obscure the polarity of that to be what you want it to be.
Yeah, I guess I never really thought of that. Yeah, my goal is to just get rid of that filament winding, to just disconnect it. It makes things a little bit easier, less worry. Let's see. Well, Bob, you had one?
I've worked with mercury rectifier tubes, but I've never broken them open. Is there much in there? Do you know how much mercury?
I don't know. I don't want to find out.
Really?
Yeah. Yeah, no, there's a fair amount, depending on the size of the distributor. Once I used to work with, about 14, 15 inch. They had about the equivalent of about a quarter's worth.
Wow. Yeah.
Well, the place was probably should have been buried.
For little things. Yeah, I worry about that too. I've got mercury thermometers. I've got mercury switches. I've also got 8008s or 872 mercury vapor rectifiers. The great big ones, 8008s.
Yeah, with the big cap on top.
They're huge.
Yeah, they're huge. For many years I was in broadcast engineering and chief engineer of stations throughout the country. And one of the nicest transmitters was an RCA 10H. And the 10H was a 10 kilowatt AM broadcast transmitter. And the cabinet itself, just with a high voltage, was about this wide, 6 feet, and had like 4 cabinets. It went down, and it had 8 from the 800 mercury vapor in a 3-phase arrangement. 8 of them? Yeah. No, they had 6, either 6 or 8. And they just blow real good. And then at when I was in Seattle, as engineer for a couple of stations there, we had a listener-supported FM with the call sign CRAB, C-R-A-B. CRAB was run on a shoestring. CRAB never had enough money to do anything, and everybody was like, the other engineers would donate time, help us there to donate here, whatever. They converted an old TV transmitter to the FM. And this thing never came with a plate transmitter, so high voltage supply. So rumor has it that they liberated a pole transformer that was 10,000 volts AC on one side to step it down to 240, and they reversed it. And they had on the wall a 4x4 sheet of plywood, and I swear it must have been about 60 to 80 1007 diodes mounted on this plywood, piece of plywood, with the resistors and the capacitors, of course, they brought things out and stuff. And they ran that through this liberated pole transformer for the high voltage power. They needed somewhere around 12,000 volts, I think, or 15,000 volts to run the transformer. But so for protection, all they had was a little door. You just open up this, it was mounted on the wall, they had 2 short doors like that, and you open up this plywood door, and there's your high voltage supply right there.
I am so glad to hear you say that, because some of the power supplies for your kilowatt amplifiers have a bridge rectifier with a string of 10 diodes for each leg. So that's 10,000 volts.
The FCC did inspect them, and they said, you've got to have a unit on the plywood door. So if you opened up the door, the high voltage would, shut down.
Yeah, they sure are pretty, but it comes at a pretty high price. There's danger and there's high voltage. Yes?
Long ago and far away, I also did a stint in broadcasting as an engineer, and we had a 10 kilowatt CGE, Canadian General Electric transmitter. It was an old beast, and you could see the flame marks and the fires and stuff. But it amazed me for hours, much to my boss's chagrin probably. I'd go in at night for a midnight shift, turn off all the lights, and watch the mercury rectifiers modulate with the audio. And it was truly mesmerizing. Again, much to my boss's chagrin.
We put Kentucky Fried Chicken dinner on the finals of one auxiliary transmitter just to keep the Kentucky Fried Chicken dinner warm. And then the main transmitter went off and we had to use it. We forgot that the Kentucky Fried Chicken dinner was still sitting on the finals. It was 4.400. So a pair of those things. And, so the styrofoam cup with the mashed potato was kind of melted and all over.
Well, but it smells good though.
Oh, yeah, it smelled like fried chicken.
Yeah, they sure are pretty. Well, anyway, the last two projects that I did were the Hewlett-Packard audio oscillator and the Hewlett-Packard vacuum tube voltmeter. I've got my Holocrafters HT37 transmitter sitting at home with two solid-state modules. It's been working wonderfully for the few times I've decided to pull it out and put it up on the table and get it operating. I was going to bring those in, but I figured, well, pictures would be good enough. So yeah, do this. Consider it for your tube stuff. You'll save a couple watts of heat. You won't have to worry about your transformers zorching. Things will be a little bit cooler in summer, and for the most part, you won't know the difference. And anything else? Yeah.
Do you ever use isolation transformers in your work? Isolating around?
Sometimes. Yeah, for tubes, tube devices. Oh, someone also mentioned hot chassis equipment. They asked if there's any consideration for replacing rectifier tubes in hot chassis devices, like the what is it? The Holocrafters S51, the S56. There's a couple of those that have got the no transformer hot chassis. Same thing. Diodes will work fine.
Don't those have use a series filament arrangement, and you have to
yes.
compensate for the voltage drop of the rectifier
Yeah,
filament?
that's right. There's no rectifier filament all of a sudden. Yeah, that issue did come up.
Yeah, like a 35W4 or something.
Right, right. Yeah, that issue did come up. But the diodes themselves, no problem. The filament, yeah, you're right, that is a problem. Okay, well, that's all I've got. They sure are pretty.
Yes, they are.